Welcome back, everyone. Let's continue where we left off last time by actually now preparing our data and fitting a k-means clustering model. Let's get started and head it back to the notebook. All right, here I am at the notebook where we left off last time. We finished our data visualization. We can check out the head of the data frame and recall that we actually have this issue of categorical data. And when it comes to k-means clustering, intuitively, we know that we can't really use this categorical data because everything is going to be based off of distance metrics. We're always going to be iterating and checking which point has its closest cluster center for reassignment, which means in order to actually check that distance to the cluster center, we need things to be numeric. I can't really check the distance between something like housemaid and married, but I can check the distance between a 0 or 1 value in job and a 0 or 1 value in marital status, which means just as before, we need to actually get dummy variables. And we also don't really need to worry too much about dropping the first value with the issues of the dummy variable trap or multi-collinearity, because this is unsupervised learning, which means we're not going to get some sort of coefficient attached to these dummy variables, which means we can just easily say x is equal to pd get dummies, and I'm just going to pass in the entire data frame. I don't even need to worry about separating out a y label because there is no y label. This is unsupervised learning. It's all features. And now I have x, and I have campaign, p-days, previous, etc., and a bunch of other features. But notice now I have 65 columns. So if you scroll all the way to the right, you see now all these categorical columns, which is exactly what we want. And we don't need to worry too much about subscribe no, subscribe yes, essentially duplicating each other for the case of k-means clustering. So what we're going to do now is have to scale our data. Why do we want to scale our data? Just as before, recall we're dealing with distance metrics. And if you have one metric or feature that's valued between 0 and 1, but then you have some other ones that are in completely different feature spaces, such as going all the way to 100 or maybe even in the thousands here, we want to make sure that these do not distort a particular dimension when we're trying to figure out which cluster center is closest to a particular data point. We can just alleviate this issue completely by scaling everything. So we can say from scikit-learn preprocessing import standard scalar. Then we're going to create an instance of our scalar object. So scalar is equal to an instance of standard scalar. And then I'm going to say scaled x is equal to scalar fit transform x. Now you'll notice that I've kind of changed something that we've done in the previous supervised learning lectures. In this case, I'm only passing in x because there is no y label, and I'm going to call fit transform all in one step. Since I'm just dealing with features and I want to scale everything, and there's no test data set I need to worry about in unsupervised learning, I can do this all in one line. There's really no such thing as data leakage here because there is no test set, because there is no label, because this is unsupervised learning and it's all features. So I just simply run this and I have my scaled x data, which means we're ready to start creating and fitting a k-means cluster model. To do this, we're going to say from scikit-learn.cluster import capital K, capital M, EANS, so k-means. And then you can call help on k-means, again capital K and capital M, to just see what this class entails. So this is k-means clustering, and the absolute main parameter you have here is the number of clusters. This is the k value. How many clusters are you actually going to try to form, and how many cluster centers are there going to be? The default is 8. This is a kind of meaningless default value because it's completely dependent on your data set and the domain experience necessary in order to understand whether or not the value is reasonable for n clusters. And we're going to talk about evaluating k values and number of clusters in the next lecture, so keep that in mind. And then there's other things you should keep in mind here. Recall that things are chosen randomly at the start. So if you want, you can actually pass in specific points to initiate a start, and there's also the possibility to set a seed for the random initiation. So just some things to keep in mind. There's also a maximum number of iterations. You should keep in mind that sometimes, depending on the data points themselves, k-means clustering could get stuck in a loop where certain points are kind of right in between two center clusters, and so they keep swapping classes over many iterations. So there is a default number of maximum iterations that you can run. If you had a super large data set with a ton of different clusters, so something like 100,000 points with 1,000 clusters, you may want to do more than just 300 max iterations, but these are definitely exceptions to the rules. Usually I don't have an issue with the max iterations, but if you're ever in doubt, you can always increase it with no problem. And then scrolling back here, you can see that there's different ways to compute the distances between points. Just go ahead and choose the auto compute. It's just going to do kind of a standard distance metric for you. You can also set a random state. As we recalled, things start off randomly, and if you're going to start off randomly and you want it to be repeatable, you can set a random state if you want. Usually not a big deal, and I'm going to show you why it's not a big deal later on, so I'll actually purposefully leave it as default none. But that's pretty much it for k-means. The absolute most important thing here is the number of clusters. So let's go ahead and check this out. We're going to create a model, and I'm going to create an instance of k-means. And for this particular case, I'm just going to say clusters is equal to 2. Why should we choose k is equal to 2? Right now, I don't actually know if this is a good choice. There is no kind of correct choice, but it's not unreasonable to think that for a marketing data set, there may be two groups, people I want to market to and people I don't want to market to. Is this a good assumption? We kind of don't really know yet, but it's a good starting point. So let's go ahead and say k is equal to 2. And in the next lecture, number of clusters, there we go. And in the next lecture, we'll discuss how we can actually kind of hone in on a particular k value using something like an elbow method. But we create the model, k-means, and then I'm going to say model dot, and then we have a couple of options here. We have dot fit, which is going to compute the k-means clustering. Later on, you'll also see that you have dot fit underscore predict, which is going to compute cluster centers and then predict a cluster index for each sample and return that as well. There is fit transform, which is going to compute clustering and transform the x that's passed in to some sort of cluster distance space. We actually won't be using that. And then finally, the one that we'll later be using is predict, which you pass in something like a single new row, and it's going to predict the closest cluster that this sample x belongs to. Or you can pass in multiple rows of x, and it's just going to say, based off previous clusters, I predict that this belongs in this cluster. Very similar to the idea of predicting in supervised learning. It's just that there was no label to begin with for the training. So really, when we're thinking of what we want to do, we can say is fit underscore predict, and we can think of this as just kind of the same way we think of fit transform, doing two things at once, both fitting and then transforming, such as a scaling of the data. Fit predict is both fitting the model and then predicting or returning the correct cluster labels. Technically, we don't know if these are correct. It's just the predicted cluster centers and cluster labels. So we're going to say fit predict on our scaled x, and this is going to return cluster labels. So again, I'm not just fitting the model, and I'm also not just predicting, I'm doing fit predict. And this is exactly analogous to the same idea of when we're doing scaling of fit transform. So it's first going to fit, which actually runs the k-means iteration algorithm and figures out, okay, where are the cluster's centers? And then the predict portion is going to map out these x values and then check what's the cluster center that you're closest to based off the fitting process that you just ran on scaled x as well. So you could technically break this up into two steps, model fit, model.predict, but because this is unsupervised learning and we just have the features as one giant feature data set, you might as well do it all at once with fit predict. In the exact same thinking, where you might as well just fit transform in a single step instead of saying fit and then transform, because there is no separation of train and test. So fit underscore transform for scaling is exactly analogous to fit underscore predict for unsupervised learning. I'm kind of keep hitting on this point that this is unsupervised learning, so we have this paradigm shift of what we're actually doing here. When we're saying predict, we're not technically doing some sort of forecasting. Instead, we're just saying, hey, based off the k-means cluster iterations, these are the assignments I'm giving to all the rows in this data set. And that's going to be returned in the form of cluster labels. So we run that, it runs the k-means iteration, we check out the cluster labels, and there you should see a bunch of 1s and 0s. Now, something you may have noticed if you're following along is you get maybe 3 zeros here and then 3 1s here. So why is that? In fact, if I try running this enough times, eventually I could get these to swap. Notice that I reran my fit predict, and now my cluster labels are exactly the opposite. It's 0, 0, 0, and then 1, 1, 1. But keep running this, and you'll kind of notice a pattern. It keeps clustering the first 3 to the same cluster and the last 3 to the same cluster. And you keep running this, sometimes it will switch, sometimes it won't, but what's actually going on here? Recall, these numbers are technically meaningless. It's just a cluster assignment. What is important is that the same rows are getting to assign to the same clusters each time. So it doesn't technically matter whether or not these are zeros or these are ones, or these are ones and these are zeros, because what's going to happen is the same cluster assignment is taking place. It just so happens to be that it's first assigning this cluster to be labeled 0 and this cluster to be labeled 1. But the actual difference between 0 and 1 is kind of meaningless here, because just as we noticed before, what really matters is the domain experience to come back and say, oh, this particular cluster label are people that maybe default on their loan, and these people will not default on their loan, or something like that. Again, this idea of these numbers having meaning, don't worry about it. So as I keep running this, you'll see that it kind of keeps swapping that idea. If for some reason this really annoyed you, that's where we have the actual feature set on k-means, where if you expand on this and scroll down to the hyperparameters you can add in for, let me just scroll down here. There we go. So the hyperparameters, you can set a random state equal to, for example, 101, and then that's going to make sure that these numbers will appear the same every single time. It's not really a big deal either way, it just is for repeatability. Okay, so we have our list of cluster labels. What we want to do is join that back in with our original data. So I can say x, notice I'm not saying scaled x, I'm saying x cluster column is equal to cluster labels. Run that, and then you should be able to check out x, and now we have age, duration, campaign, etc. But you'll notice there's one column all the way on the right, and it's essentially the column that we have discovered. It's almost like the discovering of the y, where we're clustering these rows as zeros and these rows as ones and everything in between. And that is how clustering works. Now, how do we actually interpret this? One thing we could do is see how correlated are other features against the clusters. We technically still don't know if k is equal to 2 was a good choice or not, but once you start zoning in on a particular k value, it's probably a good idea just to check the correlation between the features and the cluster assignment. So I can say x.core to get correlation. Again, this is Pearson correlation coefficient, so obviously age is perfectly correlated with itself, and then age is pretty much not correlated at all with duration, either negative or positive. It's essentially 0. But really what I care about is every single feature here, how correlated is it to my cluster assignment? And so what I can then say is come back up here and just ask for the cluster column. And then this is going to return every single feature and how correlated is it to your particular cluster assignment. And what would that actually mean? It means that for k is equal to whatever particular value you chose, in this case 2, you're going to be able to have some sort of intuitive understanding of what it's looking at feature-wise for correlation for clustering. And what we're going to do here is the following. I'm going to say x correlation cluster. I don't actually care about measuring this cluster correlation of itself. So lots of ways I can do this, but one way I can quickly drop it is say ILOC, go everything all the way until -1. So something to note is that the cluster is going to kind of drop out here, but we should still have subscribe no and subscribe yes. So you run that, and then you scroll down here. So you have subscribe no and subscribe yes. Nope, this is an issue that we didn't technically drop first is equal to true. So you should expect these to be mirror images of each other. That's not a huge deal, but in your analysis, in your report, it's just something to note out. It's kind of just duplicate information. It didn't really technically affect the model. It's still learning the same thing. That's why they're perfect mirror images of each other. But it makes sense that subscribed no should be the exact opposite of subscribed yes. So whether or not it's kind of helpful to think about it that way is kind of up to you. But now that we have these correlation values, would be a good idea to maybe sort them. So I can say sort values, run that, and now I can see what features are being strongly considered for this clustering process. And really what we care about is absolute correlation value. So we can see here, these values are being used quite heavily for the clustering, and also these values right here are being used quite heavily for the clustering. It just depends on how correlated these features are with the cluster assignments. And you can use Pandas to actually plot this by saying .plot kind is equal to bar. We've done these kind of plots before. You run that, and you're going to see this Pandas bar plot. It's probably a good idea to make it a little larger. Say PLT figure, fig size is equal to something like maybe 12 by 6. It's kind of a long plot. DPI is equal to, let's make it sharper, 200. And then you're going to see this nice plot here. Again, there's going to be duplicate values technically. As we just mentioned, subscribe no is going to be over here, and subscribe yes is going to be over here, just duplicating the results. But you can see what features are being highly considered as part of the clusters. And once you understand what features are important to a particular cluster assignment, then you can talk to a person that has domain experience and try to get an intuition of what these clusters actually represent. So again, this was for k-means, n number of clusters is equal to 2, and you can say, okay, now I know what features are important for separating out all this feature data into 2 separate clusters. What can I use with my domain knowledge and domain experience to understand what these 2 clusters truly represent? And again, there's nothing really there as like a definitive ground truth to check your results against. Okay, so this is just a general idea of trying to understand how the features connect to the clusters. What we still need to discuss, which we're going to do in the next lecture, is methodologies for choosing a k value. We'll talk about that in the next lecture. I'll see you there.